Imagine floating in a spacecraft 1 billion kilometers from Earth. Outside your window, a pale yellow giant looms in the darkness, surrounded by rings so vast they could swallow entire planets. Saturn, the jewel of our solar system, and your final destination. Not your final destination because you planned it that way. Your final destination because physics won't let you leave. Most people think of Saturn as that beautiful ringed planet from textbooks. What they don't realize is that Saturn represents perhaps the most absolute point of no return in our solar system. A journey there wouldn't just be difficult to reverse, it would be impossible. And the reasons go far deeper than distance. We first need to grasp just how far away it actually sits, because the numbers are so extreme that our brains simply refuse to process them. Saturn orbits the Sun at an average distance of 1.4 billion kilometers. That's billion with a B. To put that in perspective, when you look at Saturn through a telescope tonight, you're seeing light that left the planet roughly 80 minutes ago. A simple radio message saying, "We've arrived," would take over an hour to reach Earth. And the response? Another hour back. But let's make this more tangible. If you could somehow drive a car to Saturn at highway speeds, say 100 kilometers per hour without stopping, it would take you over 1,600 years. That's longer than the time between the fall of Rome and today. Your great-great-grandchildren, dozens of generations removed, would still be driving. Now consider this. Mars, our next target for human exploration, is roughly 55 million kilometers away at its closest approach. Saturn is 25 times farther. Every challenge we face getting to Mars, the radiation, the isolation, the supply problems, multiply all of it by 25. Then add new problems we haven't even imagined yet. The journey to Mars takes 6 to 9 months. A journey to Saturn? Using conventional rocket technology with optimal planetary alignment, we're looking at 6 to 7 years, one way. Think about that. 7 years in a metal container hurtling through the void. 7 years of recycling every drop of water. 7 years of cosmic radiation bombardment. 7 years of watching Earth shrink to an invisible dot. And that's just getting there. Here's where it gets sobering. The distance isn't even the main problem. The real issue is energy. Getting a spacecraft to Saturn requires an enormous amount of fuel. But here's the brutal mathematics of space travel that most people never consider. Every kilogram of fuel you bring needs more fuel to move it. And that additional fuel needs even more fuel to move itself. This is called the rocket equation, and it's one of the most unforgiving laws in physics. To accelerate a spacecraft to the speeds necessary for a reasonable Saturn transit, then slow it down enough to actually stay there rather than flying past, requires fuel quantities that border on the absurd. The numbers break down so badly that engineers had to invent an entirely different approach. That approach is called gravity assist. Instead of carrying enough fuel to reach Saturn directly, spacecraft like Cassini used the gravity of other planets as free acceleration. Cassini launched in 1997 and didn't arrive at Saturn until 2004. 7 years of looping through the inner solar system, swinging past Venus twice, Earth once, and Jupiter once, stealing tiny amounts of momentum from each planetary encounter. And Cassini was an unmanned probe weighing about 5,600 kilograms. A crewed mission to Saturn would need to be orders of magnitude heavier: life support systems, food for years, water recycling, radiation shielding, sleeping quarters, exercise equipment, medical facilities, spare parts for everything. The mass adds up catastrophically. The more mass you try to move, the more fuel you need. The more fuel you need, the more mass you have. It's a spiral with no clean exit. But let's imagine we solve the propulsion problem. Let's say some future breakthrough gives us engines powerful enough to reach Saturn in a reasonable time frame with a reasonable amount of fuel. Now the real nightmare begins. Cosmic radiation in deep space is nothing like what astronauts experience on the International Space Station. The ISS orbits within Earth's protective magnetic field. It's shielded. Astronauts there receive about 150 millisieverts of radiation per year, roughly 50 times more than the average person on Earth, but still manageable. Beyond Earth's magnetosphere, that number explodes. On a journey to Saturn, astronauts would be bombarded by galactic cosmic rays and solar particle events with essentially no protection. We're talking about exposure levels of 600 to 1,000 millisieverts per year or more. Over a 7-year journey, that's 4,000 to 7,000 millisieverts of cumulative exposure. To put that in context, NASA's current career limit for astronauts is 1,000 millisieverts total. A single round trip to Saturn would exceed that limit 4 to 7 times over. The biological consequences are devastating. DNA damage accumulates, cancer risk skyrockets, cognitive function degrades. Studies show that cosmic radiation causes measurable brain damage, affecting memory, decision-making, and reaction time. The longer the exposure, the worse it gets. And here's the catch. There's no practical shielding solution. The particles are so energetic that stopping them requires either enormous masses of material or active magnetic shielding systems that don't yet exist. Thick armor actually makes things worse by generating secondary radiation when high-energy particles slam into it. By the time astronauts reached Saturn, their bodies would already be fundamentally compromised. Now let's talk about what happens to the human body in microgravity over these timescales. On the ISS, astronauts spend 6 months in orbit. Even with 2 hours of daily exercise, they return to Earth with measurable bone loss, muscle atrophy, and cardiovascular deconditioning. Some never fully recover their pre-flight bone density. A Saturn mission means years of weightlessness, not months. The numbers become terrifying. Bones lose density at roughly 1 to 2% per month in microgravity. After 7 years, we're potentially looking at bone loss exceeding 80%. Your skeleton would become so fragile that ordinary movements could cause fractures. Standing up in any significant gravity would be out of the question. Muscles follow a similar trajectory. The heart, which is itself a muscle, begins to shrink and weaken. Without gravity forcing it to pump blood upward, it adapts to an easier workload. After years in space, it would struggle to maintain blood pressure against even reduced gravity. The eyes change shape as fluid pressure in the skull increases. Vision problems are already documented in ISS astronauts after relatively short stays. After years in microgravity, permanent vision damage becomes almost certain. Your immune system weakens. Your balance system, designed to work with gravity, becomes confused and eventually non-functional. Dormant viruses reactivate. Wounds heal slowly. After 7 years of transit, the human body would be transformed into something barely capable of functioning in any gravitational environment. You might think the solution is artificial gravity, a rotating spacecraft that simulates Earth's pull. In theory, yes. In practice, the engineering challenges are staggering. To generate comfortable artificial gravity without making the crew sick from Coriolis effects, you need a spacecraft with a rotation radius of at least 100 meters, spinning at a precise rate. Building, launching, and maintaining such a structure with current technology is effectively impossible. The mass requirements alone would make the fuel problem exponentially worse. And even if we could build it, the spacecraft would still need to spend years in deep space, exposed to radiation, with systems that must work flawlessly for nearly a decade, with no possibility of resupply or repair from Earth. A single critical failure and the mission ends. Not with rescue, with death. Let's pause here and acknowledge something. Everything we've discussed so far assumes the goal is simply reaching Saturn, getting into orbit, surviving the journey. We haven't even touched on what happens when you arrive, and that's where the mathematics become truly impossible. Saturn has no solid surface. It's a gas giant, a world of churning hydrogen and helium that gets denser and hotter as you descend until the pressure crushes anything we could possibly build. You cannot land on Saturn. You cannot even get close without being destroyed. But let's say the mission goal is simply to orbit Saturn and study its moons. Titan, with its thick atmosphere and liquid methane lakes, Enceladus, with its geysers of water ice suggesting a subsurface ocean. Even then, returning home presents an insurmountable problem. To leave Saturn's gravitational influence and head back to Earth, you need to accelerate, significantly. And remember the fuel problem? It's actually much worse than we discussed. You don't just need fuel to get to Saturn, you need fuel to slow down when you arrive. Then you need fuel to accelerate again for the return journey. And you need fuel to slow down when you reach Earth. Each stage requires massive amounts of propellant, and all that return trip fuel has to be carried with you from the beginning, which means you need even more fuel to move that fuel. The rocket equation is merciless. For a crewed round trip to Saturn with reasonable transit times, the fuel-to-payload ratio becomes so extreme that the mission requires either a spacecraft the size of a small city or propulsion technology that doesn't exist. This isn't a matter of engineering creativity. It's a hard physical limit. There's another factor that rarely gets discussed: communication. At Saturn's distance, light itself takes 70 to 90 minutes to travel one way, depending on orbital positions. A simple conversation with mission control means speaking, waiting nearly 2 hours for your words to arrive, then waiting another 2 hours for the response. In any emergency, you are alone, completely alone. If something goes wrong, there is no real-time guidance, no immediate support, no rescue. You must solve every problem with whatever resources and knowledge you have on board. And you must solve it fast enough that the problem doesn't cascade into total system failure before you can communicate that anything went wrong. The psychological toll of this isolation is almost impossible to predict. Humans evolved as social creatures, dependent on connection. Years of confinement in a small space with a handful of other people, with no possibility of escape, no new faces, no change of scenery, and the knowledge that Earth is so far away that meaningful help is impossible. Studies on Antarctic research stations and submarine crews show that even much shorter periods of isolation lead to depression, anxiety, interpersonal conflict, and cognitive decline. A Saturn mission would push human psychology into completely unexplored territory. So where does this leave us? Saturn is not like Mars. Mars is extraordinarily difficult. Saturn is effectively impossible with any technology we can reasonably project. The distance is too vast. The energy requirements are too extreme. The radiation exposure is too lethal. The physiological damage is too severe. The return journey is mathematically unfeasible without propulsion breakthroughs that may never come. A human who traveled to Saturn would arrive as a radiation-damaged, physically deteriorated shell of their former self, orbiting a world they could never touch, with no way home. This isn't pessimism, it's physics, and physics is non-negotiable. Perhaps in centuries to come, technologies will emerge that make the impossible merely difficult. Nuclear fusion propulsion, advanced radiation shielding, artificial hibernation, spacecraft that can harvest fuel from Saturn's moons or atmosphere. But with everything we know today, and everything we can reasonably expect to develop in the coming decades, Saturn remains what it has always been. A beautiful jewel in the night sky, forever out of reach. There's something profound in that limitation. We live in an age where we've grown accustomed to conquering every frontier. We've climbed the highest mountains. We've descended to the deepest ocean trenches. We've walked on the moon. But the universe doesn't care about our ambitions. The distances are real. The laws of physics are immutable. And some places may simply be beyond human reach. Saturn reminds us of our scale, of our fragility, of the fact that even our most magnificent achievements are tiny compared to the cosmos we inhabit. Maybe that's not a tragedy. Maybe it's a reminder to treasure what we have, this pale blue dot suspended in the darkness where all human history has unfolded, the only home we can ever truly return to. I hope you enjoyed this video. If you'd like to see more explorations of the boundaries of human space travel, consider subscribing. I'll see you next time.